Hey guys, welcome to lecture number 15. So in this lecture, we will be talking about linear approximation, differentials, and error propagation, if you want. Well, this is one of the lectures that will not be included in your gateway exam or in your midterm exam, but it will be very relevant to your final exam. And in your final exam, you will see questions regarding linear approximations and differentials. So please take this lecture and the next one seriously. So over the course of today and Wednesday, we will be talking about this. I'd like to say that I didn't have a chance to cover it in great detail as I wanted to last semester. As you have noticed, I sent you a video, and last semester I did I included linear approximations and differentials with related rates. So I think I covered only like 20 minutes of it, so it wasn't too much. Okay, all right, let's get started. So I would like to start with the linear approximation first. And let's see this guy, okay. All right. So, linear approximation. Let's see what this is all about. So, first, look at this equation. We consider a function f, which is differentiable at the point C, right? And we know that, and of course, since the function is differentiable at the point C, we can compute the derivative at that point, right? Obviously. And we know that the equation of a tangent line at the point of coordinates C, f of C, is given by the equation that you see, right? Is y equals f of C plus f prime of C times x minus c, right? As you can see, the derivative at the point is nothing else than the slope of the tangent line. So this is the equation, as you already know. All right, so the question is the following we would like to answer. So the question is the following. So we know that the tangent line closely approximates the shape of y equals f of x, right? In the immediate neighborhood of c f of c. And now the question is, if x1 is near c, that is the thing that we're interested in. So if this guy here is near c, what can we say about f of x1? So f of x1 will be near what? That is the question, right? So what do you think? F of x1 will be near what? If x1 is near c, what do you think? What does your intuition tell you? F, exactly. So intuitively, f of x1 should be close to f of c. Okay, but the answer is that f of x1 must be close to the point on the tangent line to y equals f of x at the point x equals x1. And that is, and we know that the equation of the tangent line is this one here, right? The equation of the tangent line at this point is this one here. Well, guess what? This means that f of x1 is approximately, right? F of c plus f prime of c times x1 minus c. Right? So that This is what we're looking for. And well, we will call this the linearization of the function f at the point x equals c. So that's what we call this. So this is the linearization of the function f at the point x equals c. And we write this as in this way. So the linearization of the function f at the point x equals c will be L of c. So let me write it. So it's L of x, sorry, equals f of c plus f prime of c, so the derivative, times x minus c. So that's the linearization. So keep that in mind. At some point, I'll give you problems. Well, I'm going to ask you, given this function, find the linearization of the following function at the following at a certain point. Well, that's what we're going to do. Let's see an example. Well, look at this. So let me have this example in mind. So let's see example here. Which says the following. So we like to find the linearization, right, of this function f of x equals 1 plus sine of x at the point 0, 1. So how should we proceed? So think about it. You need to, as you can see, you already have the formula above. Exactly. So we need to identify the variables. All right, let's see. Who is C in our case, right? And who is f of c? Well, who is c? Exactly. So like Nolan says, c is 0 and f of c will so the linearization of the linear approximation, if you want, or linearization is the following. So as you can see above, L of x, sorry, is nothing else than just f of c plus f prime of c times x minus c. So let's keep this in mind. Okay, and now we will identify c is 0 in our case, right? And now the only thing we need to compute is we need to evaluate f at the point c equals 0. So it will give us f of c is 1 plus sine of 0, which is 1. So this is c here, and this is f of c. So that's the point. So let's see, let's identify our function. So our function f of x is 1 plus sine of x. An easy computation of the derivative will give us that f prime is cosine. And of course, f prime of c, right, will give us what? Will be cosine of 0, right? Because c is 0. Which is 1. And now we have identified all the elements of our linearization. So we know who f of c is, we know who f prime of c is, we know who c is, and then we can actually write it. So by writing in this way, this will imply that this is nothing else than just, well, by just doing the computations, it will give us that this is nothing else than just 1 plus x. So in other words, the linear approximation of 1 plus sine of x around the point 0, 1 is nothing else than just 1 plus x. So you can write this as 1 plus x if you want, as approximately 1 plus x near the point 0, 1. So roughly speaking, you can say that. It's easier to work with this function rather than 1 plus sine of x. Okay. Like I said, the only thing you need to know is just the linearization formula. All right, now let's talk about differentials. And let's see what this, because we have talked about what dy over dx is, but we actually, I would like to touch this subject because it has a lot of depth into it. And well, over the course of this week, we would like to see what this dy or dy over dx actually means. All right, so as you have noticed so far, sometimes we write the derivative of y with respect to x as dy over dx, right? Or y prime of x, remember? So that's how we write the derivative of y with respect to x. So this or this. Well, we would like to see what is the meaning of these quantities. And we would like to describe this in terms of linear approximations. Okay. All right, so what we're going to do is the following. So first, let's consider the tangent line to the graph of f at the point of coordinates c and f of c. So we know that the tangent line, the tangent line is given by this equation here, y equals f of c plus f prime of c times x minus c. Right? So that's the equation of the tangent line. At the point c f of c. Oops. So that's what you need to know. And now, well, but we can also use this as an approximation for the graph. So let's see, what do we have? When this is used as an approximation to the graph of f, well, this means that the quantity x minus c is called the change in x. So this is important, right? The change in x. So this guy here is this quantity. And well, let's denote this by delta x, right? And also, when delta x is small, the change in y, which will be denoted by delta y, right? So the change in y can be approximated in this way. Look, so delta y will be nothing else than just f of c plus delta x minus f of c, which is approximately f prime of c times delta x. Anyway, that's and also you will see later on that this will be related to what we will call the mean value theorem. We will learn this, I think, after this chapter. We'll learn about more about qualitative properties of differentiable functions, and we will learn about the mean. One of them will be the mean value theorem, which will be an amazing tool for differentiable functions, including finding the roots of functions or their derivatives and so on. It will be, let's say, an analog of the intermediate value property, but for differentiable functions. Well, roughly speaking, exaggerating a bit, but. All right, so once again, when delta x is small, the change in y, which is denoted by delta y, can be approximated in this way. F of x plus f of c plus delta x minus f of c, which is approximated by f prime of c times delta x. And we call this, sometimes, we call this the incremental approximation formula. So keep this in mind. Also, like I said, well, I would like to stress that again, this will be related to the mean value theorem for differentiable functions. Anyway, some way. All right. And now let's see. Let's see what will happen for such an approximation. Well, for such an approximation, right, for that you see for of delta y, well, for such an approximation, delta x is traditionally denoted by dx. And this is called the differential of x. So that's what, this is what differential actually is. Okay, so now let me be more specific now. If a function f is differentiable at the point x, the expression f prime of x dx is called the differential of y, and it is denoted dy. So in other words, we can write dy as f prime of x dx, which is y prime dx. So that's what we call the differential of y. So this expression right here, right? And we have also this, right? Anyway, let me say one other thing. We will use this thing with the differential when we will integrate. So in other words, when we will find not the derivative of functions, when we will find the antiderivatives of functions. So keep that in mind. Okay. So once again, let's recap now. And just to be clear, we will have the following. So delta x, which is dx, will be the change in x. Delta y, which is the rise of f that occurs relative to the change in x. So pay attention, and we have seen how this will how this occurs, right? And dy will be the rise of the tangent line relative to the change in x. So relative to delta x, which is dx. So the rise of the tangent line. This is important here. Tangent line. All right, so these are the expressions we have in mind. And now let's see some examples. Okay. I want you to look at this example and think about it for a minute or two. So the example says the following. So let's consider this parabola, the simplest parabola possible. So we take y equals x squared, and we need to find dy, right? Like I said, dy is nothing else the rise of the tangent line relative to the change in x, which is delta x. So we need to find dy when x equals 1 and dx is 0.01. And we would like to compare this value, delta y, when x equals 1 and delta x equals 0.01. So what should we do first? Yes, Dylan, you want to say something? So what should we do first? Exactly. So we need to differentiate. So we need to take y, we need to differentiate first x squared. All right. So we're going to consider y equals f of x, which is x squared, right? And we need to differentiate this to find dy. So dy will be f prime of x dx, which is 2x dx. And then what? We will evaluate dy at the point, what point? At the point x equals 1 and delta x, which is dx, 0.001. So let's do that. And look what we have. So dy, which is dy evaluated at x equals 1 and dx equals 0.01, will be 2 times 1 times, right? Because x equals 1 and delta x is 0.001, which will give us, by some computations, this will give us like 0.002. Anyway, this is just algebra. I'm sure you can do it. But now here comes the question. How do we evaluate delta y? So what do you think? Because that's what we're interested in. So delta y. Is what? What did we say about delta y? So the big question here is, who is delta y? How do we evaluate this guy? What do you think? Exactly, like Jasper says. So we have f of delta y, it will be f of x plus delta x minus f of x. So exactly, that's how we will evaluate delta y. Well, now we just need to plug it in. So when x equals 1 and delta x is 0.01, and delta y evaluated at these two will give me f of 1 plus 0.01 minus f of 1. Okay. Now let's just plug it in and it will give me nothing else than just, well, this is just algebra. We know that f of x is x squared, so this this difference will be equal to 1.01 everything squared minus 1 squared, which is, by some algebra, and I'll leave this to you, will give us this result. So that's what delta y is. As you can see, delta y you can remark the difference between delta y and delta x, right? They're not the same. Okay. Now let's see what kind of operations do we have with differentials. Well, as you can see, this differential is more or less like acts like a derivative. So you would expect that similar properties will be valid. So let's see. Let's see more properties. Well, each of the differentiation rules that we studied earlier, can be written in differential form, right? Because instead of the derivative, you can write, so when you have u prime dx, you can write this as du. So for example, so let me just give you the example of these two functions, u and v. So these are differentiable functions of x. And by the definition of differentials, du is u prime dx, and dv will be v prime dx. And also, let's remember we had the product rule, for example, DUV was, well, is nothing else than UV, everything prime. And by the product rule, right? So imagine we apply the product rule here. So, right, product rule applied here. Let me recall that UV prime is U prime V times plus V prime U. As you can see it here, this will be nothing else. So DUV is U prime V plus V plus UV prime dx. And now we know that these two commute. So this is nothing else than just VU prime plus UV prime dx. And now we will use the distributive property of dx. So we'll pass dx along each term. So this will give us VU prime dx plus UV prime dx. And now, as you can see, I will have this guy here, U prime dx is U prime, or is du, sorry. So this is du. And V prime dx here, this is dv. As you can see, we see them here. So it's a v du plus u dv, which is u dv plus v du. So once again, we can say that if we use the notion of differentials, so if we want to write this in differential forms, we will have that duv is u dv plus v du. Keep that in mind, right? So we start from here, and we ended up all the way here, right? And now let's see another example. And the example that I have in mind is the following. So find dy if y is f of x, which is x squared plus 1, everything to the power 1/2. Okay, think about it for a bit. So what do you think? Who is dy? dy is what? What did we say? Hmm? Well, exactly. dy is f prime of x dx. Exactly, that's it. Okay, so let's write this. So dy is f prime of x dx. And now we can compute the derivative, and there is no problem, right? We can apply the chain rule here. When we compute the derivative, I think we've done this, right? Remember that. So here we apply the chain rule. So remember we have something like f of u of x, everything prime, which is f prime of u of x times u prime of x. Well, in our case, u of x is nothing else than just x squared plus 1, right? So, and f of well, I should have said differently here. G of, okay, let me change that so that you guys can see better. I mean here, let's say G of u of x, so that this is G prime. And now in our case, G of x is the square root of x, right? Or x to the 1/2. And of course, using this, you'll get the derivative of the square root, which is 1 over 2 square root of x, but u of x, right, is x squared plus 1, which you will find it here. So this portion here, by applying the chain rule, is nothing else than just g prime of u of x. And this portion here will be nothing else than just u prime of x. And of course, by doing some algebra, elementary algebra, you'll end up with this. Okay, okie dokie. So we will have the following. So we can say that dy is nothing else than just then x over the square root of x squared plus 1 dx. You see, it wasn't a hard thing to do. All right. Now let's talk a bit more about differentials. Let me talk a bit more. And what I would like to say right now is that the area of a square, as you know, right, is x squared, where x is the length of the side. Okay, great. As x vary, right, because we can have a square like this, then we can make it smaller and so on. So x will vary. So the length of the sides will vary. So we can consider, we can see this as, let's say, a of x is a function of x. So a of x is x squared. And therefore, we can take the derivatives so a prime of x is 2x. Or we can write it in this way. So the derivative of a with respect to x is 2x. Or if you want in differential notation, I would like you to look very carefully. You can write this as dA is 2x dx if you want. This is important. All right, so dA, let me write it again, is 2x dx. We can write it in this way. And now let me give an example. Let's see another example. Okay, I would like you to look at this problem. It's like a word problem, more of a related rates type of problem. So think about it for a bit. So the problem says the following. So suppose a square has sides 3 centimeters long. So if the sides change by 0.1 centimeters, how much does the area change? So think about it for a minute or two. So what did we say about the area? Just look above. If x is one of its sides, or the size of a square, the area as a function of x will be equal to what? Come on, tell me. We said it previously. Please don't leave me here. Tell me, what is the area? Exactly. So the area is a function of x, right? So, ouch. So the area, okay, let me write it with red. A of x is x squared. Let's keep that in mind. So A is x squared. And now we can differentiate with respect to x as we have seen, and we can write it directly, right? We have that dA, which you guys see here, is 2x dx. And now we just plug it in, right? We know who the square has sides 3 centimeters, so x is to 3. And we know that the size changed by 0.1 centimeters. So we know that dx is 0.01. So let's see that. So it's 2 times 3, right? Times 0.01. And so this guy here is this guy here. Ouch. So these two are equal. And now this is just algebra. You see, it's 0.06 centimeters. And now I'd like to point out a remark here, right? And I would like to say the following, because this is important. I would like to notice the fact that that delta A is not exactly, dA, sorry, is not exactly delta A, right? Because the original area is, well, if the side is 3, so the area will be 3 squared, which is 9, right? And the new area, right, because if we change the side, right, then the area will change, and we'd like to see how much. So the new area will be 3, so we change the side by 0.1 centimeters. So the new area will be 3.1 everything square, which is 9.61 centimeters squared. So as you can see the difference, delta A will be 0.61, right? So I'd like you to see the difference between these two. Look at this one here, and look at this one here, right? You see the difference between them. And now let me show you a graph that I would like you to see. We would like to see how we're gonna, if we have the graph of a function, right? We would like to see how we're gonna look at the tangent line, how we're gonna interpret all these changes, delta x, delta y, and so on. Okay, so I'd like you to look at the following graph. Look at this. So you see we have the graph of f, y equals f of x. Look at it here. There's this guy here. It passes through some points, right? All right, look at it. So that's the graph y equals f of x. And the tangent line, it's this one here. Let me, or maybe, anyway, let me put it with red. So it's this guy here. So that's the tangent line. Right? that passes to, so at the point y, the point x in f of x, right? So this is the point here. Of coordinates x and f of x, right? So that is the tangent line of the point x equals f of x. We know how to write that, right? We have seen the equation of the tangent line. All right, and now we're going to increment on the y-axis and on the x-axis. So we would like to see the change from x and the change from y. So as you can see, we will have the change will be x plus delta x, right? And the difference, so the distance between x and delta x. So here we have the point x and delta x. Here we have the point x. And the difference, as you can see, it's expressed here as delta x. From here, right? And the same goes for, like I said, the point x will have a correspondent on the y-axis, which let's say it's y. And the point x plus delta x, as you can see here, will correspond to y plus delta y, which is somewhere around here, let's say. That's the point, you see. All right, so we'd like to measure the difference between them. So between y and delta y will be delta y, as you can see it here, right? This guy is delta y. Oh, sorry, dy, I'm sorry. And here between y and delta y will be, just like we had on the y-axis, this will be delta y. Okay, so that's the classical picture that you guys, so we have the graph of a function, we take the tangent line, we can see who all these things are. Well, why am I doing all this? Because I would like to make some estimates for the let's say for the linearization of the function. I would like to see if what happens to these estimates, and in fact, when I make these estimates, what will happen with the approximation of the function. So, in other words, let me say it. Let me talk about error propagation. Let's see what this is. What this is all about. So when making estimates, it's very likely that an approximation can be too large or too small, right? As we have seen. Well, for this, we will use what we call error propagation to describe the error that accumulates from other errors in an approximation. And we would like to see what this is all about. So keep this word in mind. So error propagation. Like I said, let me repeat that. So we would like to describe the error that accumulates from other errors in an approximation. Okay. And first, let me start with the following. So first, if x represents the measured value of a variable, right, and x plus delta x represents the exact value, well, guess what? We can write delta x as x plus delta x minus x, right? So that's the error of measurement. And now the propagated error of x, so this guy will be nothing else than just delta f, right? If we have delta x to be the error of measurement, then the propagated error at x is defined as delta f, which is, as you can imagine, f plus delta x minus f of x, right? So we have this guy here. minus f of x. So that's what the propagated error is defined. This is how we define it, right? Keep that in mind. All right, now let's see an application, an example. So it's again a word problem, a very interesting problem. And the problem says the following. So the radius of a ball bearing is measured to be 7/10 inches. If the measurement is correct within 0.001 inches, well, 1/100, we would like to estimate the propagated error in the volume V of the ball bearing. Ooh. All right, so we have a ball. So imagine that this ball is like a sphere, right? And we're asked about the volume. So look at this guy here, volume V. So this volume will be like some kind of a function of R, right? And remember the volume of a sphere, let's call it V of R, is what was it? It's 4/3 pi R cubed, right? Okay. So in our case, what is the radius R? And what is the measurement, delta R? So what do you think? So exactly, like Jasper says. Well, pay attention here a bit. Well, almost right. So look. So the volume, as we have seen, is 4/3 pi R cubed. The radius is given. Look at this. Look. This is R. Well, as you can see it here, it's 0.7. And the measurement, if the measurement is correct, well, you see the error, right? So delta R will be less than this, not quite equal. So if the measurement is correct, so we will have that delta R in absolute value will be less than 0.001. But now we would like to estimate the propagated error in the volume. So when we hear about the propagated volume error in the volume V, we would like to estimate delta V. So in other words, who is this guy? And delta V is what? We said, look above. Look here. See the propagated error? Look at this guy. So the propagated error of a function f at the point x is what? Is delta f, which is equal to x plus delta x minus f of x. And so in our case, is what? Is nothing else than just, look here, delta V is nothing else than just V plus V of R plus delta R minus V of R. Okay, but this can be approximated by what? What can you tell me about this guy here? This guy here, what can you tell me about it? V of R plus delta R minus V of R can be approximately what? Can you tell me? We said this. Exactly, like Nolan says, it's V prime of R times delta R. Great. So I can approximate this difference in this way. Well, as you can see it here, that's great. And now we know who V prime of R is, so we can compute the derivative. So let's do it. Let's see it here. So as you can see here, the derivative, let me write it here, V prime of R is nothing else than what? Is nothing else than just, so it's 4/3, let's do it, times 3 pi r squared, which is 4 pi r squared, right? So that's the derivative. As you can see it here, right? We know who delta r is. So that's the derivative, right? Evaluated at the point r equals 0.7. So this guy here, this is nothing else than just v prime of 0.7. And this guy here, right? This guy here is nothing else than just this guy here. And now by just doing the algebra, we'll leave it to you. We have that by multiplying these two, this will give me, well, depends, maybe plus minus, that's why we take the absolute value, 0.00615 inches cubed. All right, so now let's answer the following question. Right, so, well, as you can imagine, we would like to see if the propagated is, we would like to answer the following question. Well, what do you think? Do you think that this propagation error is large or small? So in other words, we need to compare, what does this mean? Can you translate this? So what do we mean when we say that is this propagated error large or small? So what do we exactly want by that? So in other words, we would like to compare. So we would like to compare delta V with V. That's what we want to do, right? Okay, so the best way to do so is just taking the ratio. So so we'd like the answer is given in relative terms by comparing these two quantities here, right? Delta V and V. All right. And now the best way to do so is just comparing the ratio. So delta V over V is approximately, as we have seen, so delta V is V prime of R, delta R over V. And now we know who the derivative is. So on the top, we have 4 pi R squared delta R, and on the bottom, we have 4/3 of the volume formula, right? This guy here is V of R, which is this guy here, right? And here we have this guy here, is this guy here. So by just doing algebra, this will be 3/R times delta R, which will be equal to 3/0.7 times plus minus 0.001, which by some algebra will give me this. Well, what do you think? So this ratio, we will call this the relative error, right? And now we would like to see what is the corresponding percentage error. So the corresponding percentage error is this delta V over V, and which is nothing else than just 4.29%, right? So what do you think? Is the propagation large or small? If you multiply this by 100, it's like 4.29%. So what do you think? Is this small or large? Small, indeed. So the propagation error is small. You see how you can apply derivatives and everything in real life situations. For example, something like 20%, 15%, 10 more than 10 is considered starting to be very large. That's what we mean by large. So 4% is nothing. It's just, it's like the interest in your bank account. It's not even that. That will be considered large, but it's in this case, it's considered to be small. Yeah, something like this, or even more, I would say. Yeah, maybe even more a bit. All right, I think because I would like to cover also some of these things next time. So I think I'm gonna stop here with the lecture. I'm gonna stop early a bit. Well, like I said, let me give you some information for those of you who were not present in those 10 minutes before we started the lecture. Like I said, at 4 p.m., so expect an email from me in like an hour with all the instructions for the gateway exam. Like I said, you can take the gateway at any time you want between today at 4 p.m. and Wednesday at 4 p.m., right? So anytime, and you will have 20 minutes, right? Okay, guys, with that, see?
For the gateway exam.
Say that again?
Are we allowed to use a calculator for the gateway exam?
Yes, for a calculator is okay, but nothing else. No cheat sheet, nothing. And make sure you have Proctorio installed. Let's see, there was another question here. Yeah, the homework will, yes, all of them are due on March 17. No extensions, nothing. That's it. You had plenty of time to do those. I received some emails, some of you, which is outrageous, to be honest with you. They didn't even start the homework. They didn't even know how to log in. Anyway, other questions?
What was the, I think you had mentioned something about a like a list of formulas or something. So that wouldn't be
no, not for this one. You don't need it for gateway. For the midterm exam, you'll well, it's a take home, so it's like an open book.
And it's 10 questions, right?
Yes, 10 questions. All right, guys. Well, I'd like to wish you good luck on the test. Don't panic. It's not going to be, if you were able to follow everything that we have done, you'll have no problem. Okay. I'll see you on Wednesday, and please wait for my email. Okay. Take care. Bye-bye.